This is Prediction Profiler Part 2. We have some updates since the last time we met and talked about Prediction Profiler Part 1. The first thing is we've released a new version of the software, JMP 17. So there's a couple new things in regard to the profiler that I want to talk about today. The first one that I'm not going to show, I'll just mention. During part 1, we talked about extrapolation control, and I mentioned that that was a feature only available in JMP Pro. It is now part of standard JMP, and I'm very excited to share this with you because if you are building models, especially from observational data, knowing if you're extrapolating from your data when you're making predictions is something that you definitely need to know about. So I'm happy to announce that JMP has included extrapolation control now as part of standard JMP. I'm not going to show that, but please go back and watch part 1 if you want to take a look at extrapolation control. The second thing is the design space profiler. So this is something we're going to be talking about today. So I'll put a pin on that and we'll get to that in just a moment. The other thing I want to update you on, one of the last things I showed during part 1 is how to share your profiler. And I have a better way. I went through quite a complex way of saving out your prediction formulas and recreating it using the profiler under the graph menu. But I have since learned a better way to publish or really to share your profiler as an HTML file. So I'll show you how to do that here in a second. All right, so picking up where we left off before, this is a similar journal. I've just added in a couple things here under appearance and sharing. And then today we're going to be talking about additional profilers that are available. So let's go back and let's take a look at appearance and sharing. I went over this kind of quickly at the end of part 1, so I do want to take some time to go over some of these options for the appearance of the profiler. So let's start here. I'm going to go to this diabetes bootstrap forest model. And here's an example of a profiler. Sometimes you'll get something like this where you have multiple factors in your model and your profiler is appearing in 2 separate rows. Essentially, you have the first 6 factors here and the next 4 factors in a row below. So under the red triangle next to prediction profiler, there is an option under appearance called arrange in rows. And so the default here is 6. So there are 6 plots across in each row. So what we can do is bump that up to the total number of factors in our model, which is 10. And now we can say, okay, and now we have all of our profile traces here in one row. Removing X variables. Maybe sometimes you don't want to include all of your factors in the profile itself. You might want to include them all in the model, but maybe you don't want to display all of them in the model. Like maybe LDL and total cholesterol, those 2 factors are pretty flat. You know, maybe glucose over here. Maybe you don't want to include those in your profiler while you're trying to understand your model. So you can choose to not display those. And so we can do that by going here to the red triangle, and there's an option called Reset Factor Grid. And there's a lot of things that you can do in here. You can actually go in and change the current values that are displayed here underneath the traces. You can change the minimum and the maximum setting. You can also change the number of plotted points. Another way to think about this is, if you're going to do optimization and using maximized desirabilities, this essentially means that there's 41 possible results. There are some times where you might want to increase the resolution in the number of possible results. You can change that here. And now there's an option next called show, right? So I can choose to not show some of these in my profiler. So I'm going to unselect glucose and maybe LDL and maybe total cholesterol, maybe HDL. And then I can say, okay, and now those traces are gone. Those factors and the effects of those factors are still in my model and are being used. They're just not being displayed. And you can always bring them back by going to reset factor grids and now clicking them back on. Reordering the X variables, you can always click on any one of the factors and then drag them around. You can also come down here to the red triangle menu, appearance, and go to reorder X variables. And you can change the order in this list as well by selecting on the factors and dragging them around on this list. And that will change the order that they appear here. Also, assessing variable importance. I did show this in the previous presentation, but I'll go ahead and show this again real quick because this is another way to reorder your X variables. If you go to the red triangle, assess variable importance, you can look at variable importance this way. You can reorder the factors by the main effect importance or by the total effect. So let's do total effect here. And now these are being displayed in that order. And we can also colorize the profiler to really draw your eye into what's important. All right, now what if you have multiple Y variables? Well, let me go to that example here. This is the tire tread data set. So again, here I have multiple Y variables in this model. So in this case, we can go to the red triangle, go to appearance, and reorder the Y variables. So for example, if I wanted to see elongation first and then hardness, I can drag those around here in this list and say, okay, and that changes them here in this list. All right, so sharing. Let's go ahead and talk about sharing. I'm going to open up this example. This is one example that we talked about last time. Here we went through and we maximized desirabilities, and then we used the factor settings, remember settings, to save off the settings when we maximize desirabilities to this data table. And then we locked in spray rate at 390 and then maximized desirabilities again and saved that to our settings here. So how can I save this out for others to use the profiler, even folks who do not have access to JMP? Well, we can save it as an interactive HTML. And last time I went through a kind of a long process of saving out the prediction formulas and then recreating the profiler here under the graph menu. But there's actually an easier way that I learned recently, and so I wanted to show you that option. The first thing I'm going to do is actually get rid of some of these other things up here in my report. When I share this, I want folks to focus in on the prediction profiler itself. So I'm going to alt-click on this red triangle, the first red triangle, and just remove some of these other reports that are included here and just only include the profiler in here. Right, so we've reduced this report down. Looks like I missed one of them, but that's okay. We've removed a lot of the other things in the report. we can now go to File, Publish, and we can publish to File. File, Publish, Publish to File. And I'm just going to save it here locally on my machine and go ahead and say Publish. And what that will do is it will create this HTML file for me, right? And here's that profiler that I can now use to explore my model. And it's saved as an interactive HTML file. I can even go to these different remembered settings and apply those here in the interactive HTML. So that is much easier than saving out my formulas and recreating the graph under the profiler. So I wanted to share that one with you. All right. I think that's it for appearance and settings. Let me, close out of that and clean things up. And what I want to focus on today are some more profilers and a couple more advanced things that you can do with the profiler. So we're going to start with interaction profiler. This was a question at the end of our last session. And actually in the community post that Gail put together, she did a really good job of outlining all of the questions in the community post, but they were also recorded in the video itself. But there was the question about, okay, well, what is an interaction, and how can I tell what that looks like in my model? Okay, so this is a sample data set. All of these are sample data sets. This is the CARS 93 data set, where we're modeling the mileage of cars based on their maximum horsepower and the weight of the car. So our model contains three effects: the main effect for horsepower, the main effect for weight, and the interaction between horsepower and weight. So an interaction is essentially when the relationship between a factor and the response changes based on the level of another factor. So this relationship between horsepower and city mileage is represented by the slope. And here's my slope, my parameter estimate in my model. So as maximum horsepower increases, the city mileage decreases, right? As I'm going from low horsepower to high horsepower, my city mileage is decreasing. Right, but what happens to that slope if I change the weight of the car? Well, if I decrease the weight of the car, now there's a much steeper slope here when we're looking at the relationship between horsepower and city mileage. But if I look at cars that have a higher weight, there really is no impact on the mileage based on the horsepower. So that is really the interaction, in play here. We're visualizing that interaction as we're changing the level of weight. And if you keep your eye here on the slope for horsepower, you're seeing that change in slope. So that is the interaction. And last time I went out to Graph Builder and I showed you some overlays of these two variables, but there is actually another profiler that we can look at. And we can look at the interaction plots, which will give you this matrix of all of the factors in your model. So in this model, we just have two factors in our model, and we can look at the interaction. And what the interaction is giving you is the slope. Well, let's look at this one, which has maximum horsepower on the x-axis. And so it will show you the slope at the low level of weight, so 1695, so that represents this slope, versus the slope when we have a high weight, right? So that represents this slope here. So essentially the way that you interpret the interaction profile is if you have non-parallel lines, this is visual evidence of an interaction. So these lines are not parallel. So that is our evidence of an interaction. And let's actually go back to another model where we have more factors, back to this model here, and turn on our interaction plots. And here we have a lot more factors going on, but we can quickly look through this interaction plot to look for evidence of interactions. We're looking for non-parallel lines. So here we have an example of non-parallel lines. So blend time versus spray rate. So it looks like we have evidence of an interaction here. But here is an example of where we don't have an interaction, right? Those lines are parallel. So there's probably no interaction here between blend speed and blend time, right? So the interaction profiler, great way to quickly scan across all of your factors to see where you have interactions. I guess a caveat I should mention is you must have interaction terms in the model, right? When you build out your model, you certainly needed to put those interaction terms, those cross terms in your model. All right, so let's go take a look at a more complicated scenario. And in this scenario, I want to talk about the surface profiler and simulation experiment. And this is an example of doing robust optimization. So essentially what I want to do in this example is I want to be able to find the combination of factor settings that minimize defects given the variability in my factors, right? So I want to minimize my defects and I want to find the combination that minimizes my defects, but I want to take into account the variability around those factors. All right, so in this example, I am going to use a sample data set. I don't have it here in my journal. So actually, I will show you another new feature in JMP 17. Under the help menu, there is this new feature called Search Jump. One of the things that you can do in here is you can search for the sample data sets. So I know that there's one called stochastic optimization. And so I've started typing that in and it's pulled up this sample data set. So let's go ahead and open that up. And this is an example of another way we can use the profiler. And this is something that we talked about during the last presentation. You know, the JMP profiler, the prediction profiler can be found in many different modeling platforms, in 20 modeling platforms in JMP. And you can use it with DOE data and observational data. But another way that you can use the prediction profiler is if you have a formula, right, that represents the relationship between your X and Y's. And in this example here, this is an example of a reaction, a three-step reaction where we're looking at these intermediates, K1 and K2, and we know how K1 and K2 impacts the yield. So that's in another column here. And K1 and K2 are based on the reaction time and the reaction temperature. All right, so we're going to actually put this formula. So here's that formula. So it contains K1, K2, and the reaction time. And we're going to look at it in the profiler. So I'm going to go to the graph menu and launch the profiler. We're going to put in the prediction formula. And we're going to expand the intermediate formulas because what I want to do is not model K1 and K2, the intermediate steps. I actually want to understand how reaction time and reaction temperature are going to impact the final yield. So I'm going to expand my intermediate formulas to get this profiler here. And let's go ahead. I'm going to turn off the desirability functions. And so here are my two factors, reaction time and reaction temperature. And we're predicting yield here. So we can see what's going to happen with low temperatures versus high temperatures. and what's going to happen with quick reactions and longer reactions. And you can see this is a pretty complex interaction here between our reaction temperatures and our reaction times. So if we do want to maximize our yield, we can kind of find this space here where we have a high yield. So if we have higher temperatures, we're going to get the highest yield if we have quick reaction times. But if we're using lower temperatures, we're going to have higher yields, if we go to a longer reaction time. So if we go in and do maximize desirabilities, yes, JMP is going to find that combination of temperature and time that will give you the highest yield. However, there are other places in this model that will give me a high yield, right? There could be other temperatures and times that will give me a higher yield or a similarly high yield. So the other part of this problem is I want to understand the impact to my defect rate. So I do have a specification on yield, which I do have, it's included here in my data table. So we can come in here and do a simulation where we add in that variability around temperature and time, and we can simulate what the impact is going to be let's put in our random, and let's go ahead and simulate, and we can see what the impact is going to be on the final yield, right? So essentially we've simulated 10,000 runs by including variation around these set points for temperature and time, and we can see what the defect rate is going to be. And the defect rate is actually going to be pretty high. So if I go to another space here in my factor space, where I have a higher reaction time and maybe a lower reaction temperature, and I simulate, my defect rate actually goes down. So even though I maximize desirabilities and JMP picked a really high temperature and low reaction time, I had about around a 20% defect rate given the variability around my yield at that response. So what is going on here? Well, one thing I can take a look at is my surface profile. And so here is my surface. This is my response. And actually, let me do a couple things here to try and look at our surface a little bit better. So here we're looking at our reaction temperature, our reaction time, and our yield on this surface. And I'm going to right click on this 3D plot and go to properties. And I'm going to change this to a continuous gradient here. And let's turn our mesh on and make this black so we can see. All right, so if we go again here to maximize desirabilities, right, and we have a temperature of 540, reaction time of 0.11. You can see on our surface, we're right on the edge of failure here. And if we turn our grid on, that's essentially where we're operating here. And let me pull this back so you can see here. We're right on this tip of this surface, and we can move this around to kind of see where we're at on this surface. And we're right on the tip here. So if we have any variability, we're going to drop off on our yield when we're at that point there. However, if we're at a lower temperature, higher reaction time, so let's kind of go over here to this part, we're at a flatter part on this surface. So if we do have variability in our inputs, it's not going to impact yield as much. So one thing that we can do in this situation is we can do a simulation experiment to find that place on our surface where we're a little bit less sensitive to variability here in our inputs. So we can do a simulation experiments. Maybe we want to look at 80 runs, In each of the 80 runs, we're going to simulate 10,000 runs, and we can look at our full factor space since we really only have 2 inputs here. And we can say, okay. And so now we have this data table, which has those 80 runs in here. We can go ahead and run this Gaussian process here, which is going to build that model. Here to find, and we can optimize here on our reaction temperature and our reaction time, which will find us the combination of temperature and time that will give us our best defect rate. So now we're landing at a little bit lower temperature and higher reaction time. Okay, so that's looking at the surface profiler along with the simulation experiment to find a set point that minimizes the defects. All right, so now we're going to talk about the design space profiler and the contour profiler. And this situation is a little bit different. So in this situation, let's say I want to set limits on my factors. So I'm not necessarily interested in finding exact set points. I want to know a range of set points that are going to minimize my failures. All right, so here, this is actually something that if you're in the pharmaceutical industry and you're following QBD principles for your process characterization, a lot of times what you need to do is determine your proven acceptable range, right? So what are the ranges in your factors that are going to result in high quality product or product that meets spec? All right, so here I have this example here where I have multiple quality attributes I'm looking at. I'm looking at the yield, overall yield, I'm looking at the concentration of a couple different proteins and the final pH of the product. And I've built this model here, and I can come in here and maximize desirabilities to find the combination of set points that meet my target here for each of these quality attributes. But really what I want to know is where can I run my process to get passing material? And one thing I can look at is the contour profiler. And this is nice for, if you want to look at essentially a topographical map for each of your outputs. But what I really like this for is being able to look at an overlap of each of my responses here. The white spaces here essentially represent where I would get passing material, right? There's going to be multiple combination of my factors that will pass spec, right? And so the shaded area represents where I would fail specification on one of these responses. And so if we look at the combination of all of our specifications, the white space is where we would pass spec. But the limitation here on the contour profiler is that we are looking at the mean response. So essentially, if we're operating our process right here, we are right on the edge of failure for, I believe this is pH here. We're right on the edge of failure. Well, let's go over here for this one. This is definitely blue for the second protein here. And so if we operated our process right here, 50% of the time we would pass and 50% of the time we would fail. So that's kind of one of the limitations of using this white space. The other thing is we can only look at this in 2 dimensions at a time, right? We're just looking at pH and temperature. So if we wanted to come in here and say, we could run our process in this space here. Well, what if we now took into consideration another input to our model? Well, now we're completely in a different space. So it's hard to visualize things in more than 2 dimensions. So the design space profiler is what you can use to set the range based on overall success rate. All right, so we're going to use simulations to set a range on our factors to make sure that we have passing product. All right, so this is under the red triangle for prediction profiler. It's called the design space profiler. And essentially what we've done is we've done a simulation, and I'm going to make that connected random table here. So we're going to do a simulation of 10,000 runs. And so here's that data table with 10,000 runs where we have filled in our design space. So we can look at the scatter plot matrix of our X. So this is our design space. We have 3 factors in our model, and each point in this data table represents one of the 10,000 runs. So you can see the 10,000 runs fill out this design space. And so we've calculated each of our critical quality attributes here, right? The results for each of our Ys in our model. And then we've also determined if each of the Ys were in spec, right? So if at least one of the Ys fail, then the point is red. So we have out of spec and we have in spec results. And we can also look at this in terms of our Ys, right? So here are all of our quality attributes. And we're looking at our scatter plot matrix here of our responses. And the green box is where we pass specification for the individual responses. And the points that are in green is if we pass all 4, yield, final pH, and both of the proteins. So back here in the profiler, in our design space profiler, what we're looking at is the ranges for each of our factors, pH, temperature, and mixing speed. And we're looking at the full range that was included in the DOE. And we know we can't use that full range because we have lots of failing products. So we need to bring in these ranges. So what we can do is move inward. And each time we hit this move inward, what JMP is going to do is it's going to go and look at all of the factors and determine which factor can we make the smallest change on to result in the highest impact on yield or in spec proportion. So if I move this inward, it essentially moved the pH in just a little bit, and it unselected those rows here in my design space. And now you can see some pink points here. Those are unselected because we've moved pH in a little bit. So that small increment has increased our in-spec proportion. So what we need to do is iterate through this. So now that we've moved in pH a little bit, we can do this again. And now we've moved temperature in and gotten an improvement on our in-spec proportion. So each time you hit move inward, JMP determines what's the smallest change in X that will result in the largest change in the in-spec proportion. And essentially what you can do is keep clicking on this to move in your lower and upper bounds on each of those X variables until you get to a place here where you have a high in spec proportion, right? And these are all dynamic too, just like the profiler. So, you know, if you wanted to lock one of these in, or maybe you knew you had to start at a certain pH level, you could do that as well. So essentially you get to a place here in your in-spec proportion, you know, maybe you want to be up around 80%. But that is your in-spec proportion for the design space. So you still want to go back and do that simulation to understand what the actual failure rate is going to be if you operate in the middle of each of these ranges or somewhere within each of these ranges. So what I can do under the red triangle is I can send those limits to the simulator, right? And what we're going to do is we can add in some variability around those limits. So let's do 3 sigma on each of those. And then the other thing I want to do is I want to set that profiler at the midpoints of each of my ranges. All right, so now my profiler is at the midpoint of each of those ranges, and then I've added in variability, and now I can understand what's going to happen to the overall failure rate if I operate in the center of these limits with this variability in here. And you might want to adjust these, based on what you know about, each of these factors like pH. Maybe you want to look at the variability in the method. Temperature maybe is something that you're better able to control in your manufacturing facility, and so on and so forth. But now you can look at what's truly going to happen with your failure rate.